Okay, so this lecture we're gonna talk about the Tychonoff Theorem. And so the Tychonoff Theorem basically states that arbitrary product of compact space is compact. And instead of with the open cover formulation, we're gonna use the closed set formulation and Zorn's lemma. So before that, for those who does not know what is a Zorn's lemma, let me just give a short little lecture on Zorn's lemma. So first, a definition. A relation on the set is a subset of the Cartesian product, such that if the pair x and y is in R, we write x r y. So this is any relation. So a relation is called a partial order if we have it is reflexive and it is transitive and it is also anti-symmetry. Okay, so if we have a partial order on a set, then this is called a partially ordered set, which is called a poset. And we say a chain, a subset of X is a chain if for any two elements in a chain, either of these is true. So this or this is true, which means that we can compare them, right? We have either this or this, because a partial order does not require that any two elements are comparable, and a chain implies that it means that any two elements is comparable. Okay, and for a poset, we say this is a maximal in X if for any y, x less than equal to y implies what x is equal to y. And a maximum element is that for any element we have this. So this means, okay, maximal means that if you can compare with x and you are greater than or equal to x, then you must be equal to x. But a maximum is that we have this relation with any y. Okay, so this is the implication thing. This is the implication, okay? And here's a theorem. So the theorem, this proof would be skipped. It is in my linear algebra lecture series, and it states that the following are equivalent. So if we assume axiom of choice, then we have Zorn's lemma. So the Zorn's lemma basically means that for any poset, and every chain has a maximum. So given the poset such that every chain has a maximum, then the set poset has a maximal element. Okay, so this is the Zorn's lemma. And we're going to use the Zorn's lemma to prove the Tychonoff theorem. So recall that we say a set have a finite intersection property, and for any finite subset, the intersection is non-empty. So this is called a finite intersection property. So given a lemma, so the first lemma is that for any x a set and a collection of subset of x with finite intersection property, then there exists another collection of subset of x such that it contains A and it has finite intersection property. Also, it is a maximal. If you are another collection of subset such that it contains D and E also has finite intersection property, they must be equal to D. So we say D is the maximal element with finite intersection property. Okay? So the proof is, we first give some notations, okay? So we give notation C is element of X, C is subset of X, this is the collection of a subset of X, and this is the superset, where the elements are collection of subsets. So the elements are this as a set such that each element are collections of subsets of X. And we let this A denote the set of all the collection subset such that it contains the given A and it has a finite intersection property. Okay, so we can just consider the partial order on A of containment. Now for any chain in A, right? For any chain in A, we want to show that it has an upper bound. Then we can apply Zorn's lemma, right? So for any chain in A, right, A is a collection of all this such that it has finite intersection property and it contains this A. And for any chain in this, we want to show that it has an upper bound. So we just consider the union of all the elements in this set. Okay, well, let C be the union of all elements in it. And we first see that C must be an A. This is obvious because we have this, right? Because A is a subset of all the B's, right? And B is an A, right? So this is for any B, right? So C is obvious. Now, for finite intersection, given finally many, set elements, right? And for each C1, right, there exists a BI such that CI is in BI, right? Because, for example, C1 is in C, which means that C1 is in some B1, right? So for each CI, there is a BI such that CI is contained the element of BI. Okay, now for this corresponding collection is a finite set, which means that there exists a maximum, right? So which means that if there's a maximum, then all the C1 to Cn are in this maximum. And we know that this has finite intersection property, which means that their intersection is not empty, right? So which means that C has finite intersection, so C is an A, right? Let's see, C is A and C has finite intersection property, so C is an A. And second of all, C is the maximum for B. This is by construction, right? This is by construction. Like if we have this, then any B will be a subset of all the elements, right? I mean, no, right? Any B will be subset of contained in this, right? And then we can apply Zorn's lemma, right? So we have a maximal of A. And second of all, with this same D, it is closed under finite intersection. So any finite intersection of elements in D is still in D. And second, we see that if you are a subset of X such that you intersect with any elements in D. Okay, so A intersect D is not empty for any D in the collection, then A is in D. So it kind of absorbs all the special sets, right? It absorbs. This D absorbs all the special sets such that it intersect with all the elements here. Okay, so we have these two properties, and sorry, give me 1 second. Okay, I'm back, and okay, so we want to verify A, right? Any finite intersection of elements in D is still in D. To verify this, we let B be some finite intersection of elements in D, okay? And we want to show that this is in D, right? So we let this E, this weird looking E, epsilon E, defined as D adjoined with this B, right? Then we have this, right? So it contains D. If this has finite intersection property, then we have this, right? If it has finite intersection property, FIP, then we have this, which means that B is in D, right? If this is equal to D, right? So you're in D. And so all we have to need is to verify this as a FIP. But to do this, it's also simple, right? Like, for example, if you have finite intersection of sets that B is not in it, then automatically we have it true. So we have to like mix the B inside the finite intersection, right? So for this, because we have this, right? So it is again a finite intersection. So we're done. And for part B, we want to show that it absorbs all the sets such that it intersects with any element, right? So again, we let this be equal to A, and we show that this is FIP, then we say A is in D. But this is also easy, right? E has FIP, right, is true if we don't consider if A is not involved in any intersection. So if A is involved in it, right, for this intersection, so the first M intersection they're in D, right, by part A. All right, all the finite extension of LSM D is in D, right? We just proved this, right? So we have something in D intersect with A, which is given to be non-empty. So we're done, right? So we're done with the lemma. Okay, so let's just review these two lemmas, right? One says that if you have a finite intersection per property sets, then you have a maximal, right, with respect to the finite intersection property. And this maximal is closed under finite intersection, and it absorbs all the sets that is intersecting all the elements. Okay, so now we can formally prove the Tychonoff theorem. And as I said, right, the statement is that any collection of compact spaces, their product topology is compact. The product space is compact, arbitrary product. So the proof, we let A be a set having finite intersection property, and we show that this is not empty. Then X will be compact, right? The intersection of the closures, right, the cosets. Like if we have this, then if A is a collection subset such that each A and A is closed, right, then this will be equal to what? The closure is equal to itself, right? It's non-empty, right? And this will be shown that X is compact because by compact spaces we have by lecture 10, right? X compact if it only have any collection with closed sets such as a finite intersection, it is non-empty, right? It is non-empty. So if we have this, something more general will be prove the compactness of X. Okay? So we give an A, which means that we can pick a D, such that blah 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 D has a like we talk about this, and D contains A, right? So we will have this. D contains A implies this because, like, intuitively, right, you're intersecting more sets, right? I just lazy to write down the formal proof because I think it's easy enough to eyeball this, right? You're intersecting more sets, right? So it suffices to show that this is not empty. Because if this is not empty, then this will be non-empty, right? Because we have this containment, right? So our goal is to show this is not empty for this maximal, right? All the intersection of the closures. Now, for alpha and J, we consider the projection map onto X alpha, and then we consider the image on this D. So what we mean is that we consider the set of all pi alpha D, right? Just like defined as this, okay? We define the collection of pi alpha of D for each D and D. Now, because D has finite intersection property, which means that this collection also has finite intersection property. And to verify this, we just use this property. Okay, so let me just give the rough way. If this has finite intersection property, so suppose we have pi alpha D1 intersect with pi alpha of dk, dm, right? Then corresponding D1, dm will be non-empty, right? So we pick an x in it. Okay? So we pick x in D1, dm, right? Then pi alpha of x will be in pi alpha of, right, on this, right, in this, right? But this is a subset of intersection pi alpha of di, which shows that this is an element inside this set of order. right? So this also has a finite intersection property, and if you want to verify this, like, feel free to do it by yourself. It's a 10-second work, right? Then, okay, so now we have this is finite intersection property, which means that this also has a finite intersection property because each of those is contains this, like, right, we have this, so it also has a finite intersection property, and it's a collection of closed sets has finite intersection property because each x alpha is compact, right? Then this is non-empty, we can pick an x alpha in it, which means that we run through all the alpha in J, we give a point in X, right? Each X alpha is inside this, right? Is inside this. Okay, okay, good. So, well, you might suspect that this X is in this, right? And we will show this. If we show this, then we're done. We're done the proof. So the claim is that the first claim is that if you are subbasis of X contains X, then you intersect with any elements in D, right? So this is not empty for any D and D. So to verify this, if this is subbasis of X contains X, which means that U beta is a neighborhood of X beta and X beta, right? Big X beta, the space big X beta. And we also have, by definition, right, like for any D and D, right, if you're in this, then you are in this for any D, right? You're in this. Okay, so if you are in this, this is a neighborhood of X, but because you're in the closure of this, which means that you have an element Y such that you have a neighborhood, right, that is in UB and is also in this, right? You're in the closure of this. So from this and this, we see that from here, we see that there exists a Y in D such that pi beta of Y is equal to this Y beta, right? And this Y beta is in what? U beta, right? So Y is in the preimage of U beta, right? Like this, because pi beta of Y is equal to Y beta is in U beta. And Y is in D, right? Because Y is in D. So intersects, right? So this D is arbitrary, right? So we're done. Okay, so from here, with this claim, from part B, right? It is inside D, right? D will absorb this subbasis element that contains X. This collection D will absorb this. It will take this inside D, right? And if you take it inside, and you take any finite intersection, which is any basis element contains X, right? It is in D, right? Which means that since D has FIP, so any basis of X, U of contains X, you are in D, right? So which means that this is not empty for any D and D, right? This is a finite intersection in D, right? Finite intersection in D. So here we just have that for each D, X is in D bar. Because any neighborhood U contains X intersects D, which means that X is in D bar, but is for each of them, so X is in the intersection of all of them. So here we have done the proof of Tychonoff Theorem. It states that arbitrary product of compact space is compact. Okay? So we're done with the use of Zorn's lemma. And we assuming axiom of choice for our course, so we have this Tychonoff theorem. Okay? So this is everything, and I'll see you guys next time.